Welcome back to this course on the foundations of continuum mechanics. Today we'll be going through our final lecture in the series on foundations of continuum mechanics, where we'll be summarizing the content of this course. So let's get started. So going back to the first lecture on introduction, we mentioned that we'll be starting our journey with a discussion on tensors and finally ending that with constitutive modeling. And that's what we did. Throughout this course, we applied the prerequisites which were required for developing the various discussions on continuum mechanics. Whatever we have discussed in the course, you may already have noticed, is available as a part of the lecture notes on the website. And I hope you found the textbook and the reference book useful while understanding the concepts that were discussed in this course. You went through weekly assessments, which I'm sure helped you understand and grasp the key concepts better. And through the tutorials and various exercises, we ensured that problem solving was stressed upon and the conceptual clarity was never compromised. So let's revisit the learning objectives. So in this course, we started our discussion with the mathematics of tensors. We learned how to work with indicial notation and how to derive and interpret results which are written in the indicial notation for continuum mechanics. We rigorously defined the stress measure, that is the Cauchy stress tensor, and used that through the Cauchy stress formula to calculate the traction. And we also discussed about the invariants of the stress tensor. Then we moved on to the next module on kinematics, where strain measures were defined to help us isolate the effects of stretching and shearing from rotations. And then we spent a week each on conservation laws and constitutive models. And finally, we applied all the learning to solve a real application in fluid mechanics. What we'll do now is we will go through every week and I'll highlight the important key concepts that you have learned in this course. And you should appreciate the fact that you understand these key ideas in continuum mechanics, which has actually helped you develop a strong foundations in the subject and will help you later when you apply this to advanced topics. It must be noted that whatever we discussed was always reinforced through practice problems and through a dedicated tutorial each week. So in the first week, we started with an introduction where we discussed what continuum mechanics is, and then we moved on to the definition of tensors. We talked about the indicial notation and the idea of the free and dummy indices. That is when we defined the Einstein notation or the summation convention, which is a very important idea in indicial notation that helps us simplify expressions very effectively. We talked about the Kronecker delta symbol and its substitution property, which helps us write the vector dot product, which is used in various equations in continuum mechanics. In the second week, we defined the permutation symbol, that is the epsilon ijk, which helped us write the vector cross product in the initial notation. And then we defined the epsilon delta identity, which very effectively allows us to write product of epsilons as product of deltas, which helps in the simplification of expressions with the use of initial notation very effectively. Then we applied the use of epsilon and delta in expressions which we are used to, that is vector operations, such as the scalar triple product and the vector triple cross product. This was followed by an application of these ideas of initial notation to vector tensor operations and full tensor operations. This is where we also defined contraction, which helped us develop inner products from outer products. We ended this week with a discussion on the symmetry of tensors. In the third week, which was a part of the mathematics module, we started our discussion with matrices and determinants, all written in the indicial form, which was followed by a discussion on the transformation matrix, which is used for transforming tensorial quantities from a base to a primed coordinate system. And then we developed these vector and tensor transformation rules, which use this transformation matrix to help write the transformed measures. And we ended the week with a discussion on the key concepts, which sometimes can be very confusing, that are isotropy and invariance. In the final week on mathematical foundations, that is in week 4, we talked about the idea of linear transformations, and then we discussed about the principal values and directions, that is the eigenvalue problem, and the characteristic equation. We then defined the principal axes of the principal coordinate system, which is one of the key tools in continuum mechanics, which allows us to work in a preferred coordinate system called the principal coordinate system, which makes the mathematics quite easy. Finally, we had a discussion on tensor calculus, where we talked about tensor fields, partial derivatives, and the comma notation, which helped us develop and prove tensorial identities involving the calculus of tensors. And then we discussed about the integral theorems, that is the Gauss's and the Stokes theorem, which are quite useful when expressing integrals from volume to surface and from surface to line integrals. After completing the first 4 weeks, which formed a part of the first module on mathematical foundations, we then moved to the next module, which was a module on stress. And in week 5, after defining the idea of body and surface forces, we introduced the Cauchy stress principle, which allowed us to define the traction vector or the stress vector. And then we introduced a very important formula called the Cauchy stress formula, which allows us to write the traction vector on any cutting plane in terms of the traction vector on 3 mutually perpendicular cutting planes. And this is what helped us define the Cauchy stress tensor. Then we spent a whole lecture on discussing this Cauchy stress tensor and also gave you the cube picture, which is typically used for representing the 9 elements of the Cauchy stress tensor. Towards the end of the week, we talked about the force and moment equilibrium equations, from which we developed the local equilibrium equations in continuum mechanics and also demonstrated the symmetry of the Cauchy stress tensor. In the second week on the module on stress, that is in week 6, we started the discussion with stress transformation, where we applied the ideas of tensor transformation that we learned in the first module on mathematics to the Cauchy stress tensor particularly. This was followed by a discussion on stress maxima, because it is important to identify the maximum and the minimum normal and shear stresses in a typical state of stress. So we discussed 2 methods. One was the analytical method, which is the Lagrange multipliers, and the other was a more visual method or the analysis method, which is the method of Moore's circles. And the method of Moore's circles helps us identify the complete feasible stress space along with an understanding of the maximum and the minimum stress values. Finally, we talked about plane stresses, spherical and deviatoric split in the stress tensor, and the very important octahedral shear stress, which is typically used for plastic deformations. In the week 7, we started with the third module of this course, which was on kinematics. And the discussion on kinematics started with configurations and deformations. Then we talked about the difference between material and spatial coordinates, which is a very important idea in continuum mechanics. We solved some problems on identifying the trajectory, velocity, and acceleration fields. We talked about inverse mapping, that is going from the spatial to the material coordinate system. We talked about the Jacobian of the transformation, and then we discussed about the Eulerian and the Lagrangian description of motion. Towards the end of this week, that is in week 7, we talked about a very important idea which can sometimes be very confusing, that is the idea on material derivative. We defined the material derivative, we discussed the motivation behind it, and we demonstrated a 1D derivation of that as well for completeness. With the basic understanding of configurations, the material and the spatial coordinate systems, and the Eulerian and the Lagrangian coordinates. We then moved on to the definition of key strain measures. So for that, we started the discussion with displacement field and the deformation gradient tensor F. And then we defined the Green's and the Cauchy deformation tensors, which was followed by the definition of finite strain tensors called the Lagrangian and the Eulerian strain tensors. And then while expressing these in terms of displacement gradients, we linearized them and developed the infinitesimal strain tensor, that's our strain tensor epsilon. We spent a whole lecture on discussing the diagonal and the off-diagonal terms or the interpretation of these terms of the strain tensor. And then towards the end of the week, we had a discussion on principal strains, the volumetric strain, and the spherical and the divitoric parts of strain, along with the discussion on plane strain. And needless to say, we solved problems every week. That is, every fifth lecture was actually a tutorial where we solved problems dedicatedly to help us grasp the idea better. Week 9, that was the third week on the module on kinematics. We talked about a key idea that's called strain compatibility equations, along with the idea of the infinitesimal rotation tensor. That's the tensor omega. Before starting the discussion on fluids, we briefly revisited finite deformations and talked about the ideas of stretch ratios and the polar decomposition of the deformation gradient tensor F. We then moved on to the discussion on fluids, where we talked about the velocity gradient tensor L, the rate of deformation tensor D, and the vorticity or the spin tensor W. We showed that under infinitesimal deformations, the rate of deformation tensor D degenerates to the rate of strain tensor, that is epsilon dot. So after closing the discussion on kinematics, we then moved on to the discussion on balance laws, which basically help us develop the equations in continuum mechanics, because we always need some equations to be solved in mechanics, and these balance laws are the ones which provide the starting equations. So we developed some mathematical preliminaries by discussing the material derivative of line, area, and volume elements. And then we derived the transport theorem, or what is famously known as the Reynolds transport theorem, RTT. We then applied the Reynolds transport theorem to derive the mass or the continuity equation, both in the Eulerian and the Lagrangian forms. We then moved on to the linear momentum equation, which helped us write the local equations of motion. And this time the equations are not for equilibrium, but for a general situation where the continuum may be accelerating. We also applied the ideas of angular momentum and demonstrated the symmetry of sigma again, but for situations where the system may be accelerating. At this stage, the local equations of motion were derived in the Eulerian form, and to be able to write them in the Lagrangian form, we defined two new stress tensor, that is the Piola-Kirchhoff 1 and the symmetric Piola-Kirchhoff, that is Piola-Kirchhoff 2 stress tensor. So these are the stresses which helped us write the equation of motion in a Lagrangian form. We showed how these are related to the Cauchy stress tensor. And finally, towards the end of the week, we derived the first law of thermodynamics, or the energy equation. Finally, in the last module in this course, that is the module on constitutive modeling, we demonstrated the need of the material specific laws called the constitutive laws from both a physical perspective and from the perspective of a mathematical closure problem. We talked about some fundamental properties of these constitutive models, such as the property of objectivity or the material symmetry that need to be satisfied by the models we propose, in addition to satisfying the thermodynamics laws as well. We then spent one lecture each on elasticity, that is for elastic solids, where we discussed both linear and non-linear elastic solids. Then we moved on to fluids, where we talked about Newtonian and non-Newtonian fluids, along with the discussion on viscoelasticity, where we discussed the various models such as the Maxwell, Kelvin-Voigt, and the standard linear solid models, which are all constructed from the basic spring and dashpot models. And we also discussed the ideas of creep and relaxation, which are typically noticed in viscoelastic solids. The last lecture in the discussion on constitutive modeling was the discussion on plasticity, which is a very advanced topic, and we barely touched upon the surface of this topic. However, we gave you some understanding of what is the key process while visiting a plasticity problem. And finally, to impress upon you the fact that the foundations that you have developed as a part of this course are what you require to solve real problems in continuum mechanics. We demonstrated this through solving a problem in fluid mechanics, where we first discussed the constitutive models. We talked about the Stokes hypothesis, which allows us to simplify the number of viscosity coefficients to 1. And then we talked about some simple situations or special cases of incompressibility, steady flow, and irrotational flow. We also derived the Navier-Stokes equations, which are the well-known popular nonlinear equations of fluid dynamics. And this is when we felt ready to apply this problem to the problem of a free shear, free surface flow of water flowing down an inclined mountain, where we successfully found out the velocity and the pressure fields for the given problem using the ideas that we have learned as a part of this course. So I'm sure that now you feel ready to be able to apply whatever you have learned to your respective fields. So in the very beginning of this course, I had discussed the applications of continuum mechanics in the various fields of sciences and engineering, and I'll go through them again in this lecture. So in the field of mechanical engineering, you can apply this to any situation of a fluid flow, such as flow inside a pipe or flow around an automobile, that is typically called the aerodynamics problem. Situations dealing with heat transfer, robotics, and drones can also be addressed using the ideas of continuum mechanics. In aerospace engineering, aerodynamics and structural problems can be dealt with continuum mechanics. In the field of civil engineering, static or dynamic loads, such as the loads because of wind and snow, can be estimated well using the ideas of continuum mechanics. And in the field of mining, such as in rock mechanics or minerals processing, these ideas can be applied as well. Continuum mechanics can very much be applied to material sciences, in the field of mathematics, in biology, such as in biomechanics or biofluid mechanics, in the field of medicine, in the field of physics, such as to do with climate change modeling, tectonic flows, cosmology, and so on. And then one of the major application areas nowadays is in the field of electronics cooling or the hardware cooling, because we are trying to overclock these machines, which end up generating a large amount of heat density, and therefore effective cooling is required, which basically all boils down to the equations of continuum mechanics. Advanced fields such as vision processing in computer science, etc., also use the same fundamentals as what we have learned as a part of this course. And there's a huge overlap in the mathematical theory of these fields with continuum mechanics as well. And finally, there's a huge application of the ideas of continuum mechanics in sports science. So with the strong foundations in the field of continuum mechanics, I'm sure you can engage in these areas or any other area for that matter that involves continuum mechanics. So what we learned is that continuum mechanics is actually a language. It is a language that helps us understand the physical systems. So the language of continuum mechanics starts with balance laws, and to be able to write these balance laws, we need to understand stresses and kinematics, which are key ingredients of these balance laws. But the balance laws are not enough by themselves, so they require additionally the closure laws, which are constitutive models. So all these together result in a ready recipe for the equations of continuum mechanics. So every journey comes to an end, and so does this journey. I hope you enjoyed the last 12 weeks with us and you learned something useful as a part of this course. In case you have any feedback related to this course, or you have any queries or questions related to continuum mechanics, always feel free to get in touch with me on my email address that is given on this slide. So thank you very much and welcome to the field of continuum mechanics.